Okay, so today we're going to see intermolecular forces and intramolecular forces. So let's first start seeing why we're learning this. And we use intermolecular forces and intramolecular forces to predict the properties of chemicals which undergo the forces. So we can predict the melting, boiling point, the solubility, and the conductivity. And that you'll see based on the strength of the force. So first we're going to see intramolecular force. And this is the force which bonds together atoms, ions, and it can be in a molecule or in a compound. And they're very strong. They're much stronger than the intermolecular forces. So ionic bonds are the strongest. And when there's ionic bonds, they form ionic compounds between the atoms. And you can know that it's going to be an ionic bond because the difference in electronegativity between the elements is going to be bigger than 1.9. So for example, you got here NaCl, and the difference in electronegativity is bigger than 1.9, and therefore there's an electron transfer. They share an electron, that's what keeps them together. The two ions will be called the cation and the anion, the metal and the nonmetal, so in this case sodium and chlorine. And the cation will lose an electron and the anion will gain an electron, and that keeps them together. And now we've got metallic bonds. They form metallic compounds or alloys, occur between two or more metal elements, so it's going to be all metals. The metals were held together by their valence electrons, which roam freely in what is known as a sea of electrons. So there's no electron transfer going on or no share of electrons. It's just the fact that the electrons are roaming freely, which keeps them together. And it's referred to as the sea of electrons. That's the name of the model. The atoms of metal stay together because of the attractive forces. So these electrons are flowing around freely, and they're still attracted to their nuclei, which keeps the metallic compounds together. Now you've got covalent bonds. There's two types of covalent bonds which involve sharing of electrons, and they form covalent compounds or molecules. So the first type is polar covalent bonds. So to predict if this is going to happen, you find the difference of electronegativity, so just subtraction. And if it's between 0.5 and 1.9, it's going to be polar. So the example that we have here is HCl, hydrogen and chloride. And the difference in electronegativity when calculated is 0.96, which is indeed between 0.5 and 2. So they share electrons. H gives in 1 electron, Cl gives 1 electron, so that they both have 2. So H has 2, Cl now has 8. And that will be a full electron shell for Cl8, and for H it's 2. That's all it needs in order to be stable. So now it's stable with a partial positive side and a partial negative side. Because there's a difference in electronegativity, the electrons are going to spend more time on the side that has a greater electronegativity, yes, and less time on the side with the smaller electronegativity. So the side that is more electronegative will have a partial negative charge because electrons are negative, and the other side has a partial positive charge. And it's called polarity when that happens. And then there's nonpolar covalent bonds, and that's when the two elements have a difference of electronegativity that's smaller than 0.5, obviously bigger than 0, since we're taking the absolute value. So the example here is H2. If you take the difference of electronegativity, it's 2 H's, so they have the same at 0. and they each give an electron, and they have two. So if you remember Hofbrinkel, you'll see that it's always H2, and that's because in order to be stable, they need to have two electrons, which is what happens when there's a nonpolar covalent bond. The electrons will spend an equal amount of time on either side of the bond, and the bottom bonded atoms will be neutral. Next, we're going to see intermolecular force. And this is the force of attraction or repulsion between atoms, molecules, or ions. So this time, it's not the forces that hold, in this example, the H and the O together. It's the forces that hold the entire water molecules next to each other, and they're much weaker. If you look at a liquid, they're constantly rearranging, whereas the H2O molecule itself always stays the same. It always stays permanent, but the forces between it change. And different types of intermolecular forces give different types of melting points, boiling points, stuff like that. So the first one is the weakest one. It's London dispersion forces. They exist between all molecules, always. So polar covalent bonds, nonpolar covalent bonds, ionic bonds. And LDF increases with bigger molecule size. So why does this happen? This one's a little bit complex. There's no clear-cut like electrostatic attraction. So what happens is the electrons move randomly, and when they move randomly, sometimes they get attracted to protons around them, or sometimes they just randomly happen to crowd on one side of the bond. And what happens is called an instantaneous polarity, or an instantaneous dipole, or a temporary dipole, one of those three combinations of the words. And what happens is that it approaches another molecule, and when they come together, the instantaneous polarity will shift around the electrons on the other side, and will give what's called an induced dipole or a temporary dipole. And then they stick together like a dipole-dipole bond, or like a regular old polar covalent bond, intermolecular force. And this is an example with helium. So it's regular here, and then what's going to happen is an instantaneous dipole where you have a partial negative and a partial positive. And here's another helium atom, and when they come together, this positive guy gets attracted to this negative and repels this other positive. Same thing happens with the negative, they repel. And there's an attractive force between the positive and the negative. Here is an animation in which you see the same two helium, and we're going to see them approach. And you see that movement happening as there's repulsion between the electrons and attraction between the electrons with the protons in the neighboring particle. And you see that, and you see the repulsion. There you go. And then the partial positive dipole, and there you go. All right. Now there's dipole-dipole forces, and they occur between two polar molecules. There's going to be, in a polar molecule, we've seen earlier, there's a partial positive side and a partial negative side. And they attract electrostatically. It's just an attraction between them. Not much to say about this one. If they're more polar, so there's a bigger dipole moment, bigger difference in electronegativity, there's a bigger dipole-dipole force. There's attractive forces that happen, as this intermolecular force. There's also repulsive forces that happen. And this remains a weak intermolecular force, like all intermolecular forces are pretty weak. Now we've got ion dipole forces. This one's a little bit more complex, but it's very similar to dipole-dipole. This is when there's an ion and a molecule that has a dipole, so polar. Usually it's when there's an ionic compound, so salt in a polar solution, so usually water, so it's salt water. The positive ion can be attracted to the partial negative, and the negative ion, and also, of one molecule is attracted to the positive of the other molecule. So water has partial positives and partial negatives. And what happens is that the Cl- is attracted to the partial positive, and the Na plus is attracted to the partial negative. And as you can see, that it will induce a separation, which is when it dissolves. So we're going to see that animation here. So here you see an NaCl block, so it's not dissolved yet. And there's water all around it. And Na is going to be attracted to the partial negatives of the oxygen, and Cl is going to be attracted to the partial positives of the hydrogen. That's going to happen. And then the Na plus, so you see that it's getting pulled off by the water, and the Cl minus getting pulled off by the water, and it's dissolving. Here's a closer look, where you see that sodium has positive. Sodium's just positive here, and then there's partial negatives on the water, and then on this side over here, Cl is just negative, and you've got partial positives on the hydrogens attracting to it, similar to a dipole-dipole. And a hydrogen bond. So this is also similar to a dipole-dipole. It's very strong, though. It's stronger than dipole-dipole. Not as strong as an intramolecular force, obviously, but still strong. And this occurs between a molecule that has H, so hydrogen, and a molecule that has F, O, or N. So it's fluorine, oxygen, and nitrogen. And this happens because they're extremely electronegative. And it only happens when they have at least one lone pair in the molecules. And the force happens between the partial positive that is attracted to the lone pair of electrons. So here's an animation. So you see the partial positive attracted to the partial negative of water. These are just water molecules. Plus, minus, minus, plus, plus, minus, and they're arranged in this fashion because of the hydrogen bonding that happens. This happens in DNA molecules as well. And then these are sources or resources. This is a good book that has a good chapter on intermolecular forces. Not so much intramolecular forces, but it's still good. And that's it.